So we'll just jump right into it. So I like to just start at the basics. So what is an electrolyzer? Well, an electrolyzer is an electrochemical device which takes water and it takes electrical power, it turns it into hydrogen and into oxygen. So it uses the electrical power to split the water into its constituents, which are of course hydrogen and oxygen. There are, multiple different electrolyzer system types, and today, of course, we'll be talking about PEM only. We also have alkaline, which we won't be talking about today. And of course, there's solid oxide. There's also AEM for relatively smaller systems. But as far as the large systems go, it's going to be alkaline and PEM. And over here are some of the advantages of PEM. So it uses pure water. There's no harsh chemicals. Whereas if you know anything about alkaline, uses potassium hydroxide mixed into water at a concentration of about 25 to 30%. And PEM just uses pure water. And we have an ability to run PEM at a very high current density, which reduces the footprint. We're also able to achieve higher voltage efficiency with PEM electrolyzers, which means that we put in a lower amount of electricity and we get more hydrogen compared to how much electricity we put in there. And it's also capable to hold pressure. So the hydrogen side of a PEM electrolyzer will well, the industry standard is typically 30 bars, but you don't need a compressor to hold the pressure at 30 bars because the electrolyzer will generate the hydrogen at that pressure. And you have a turn down ratio, which what this means is you're able to turn it up and down very quickly. And you're able to increase and decrease the current density really quite fast. And of course, you'll be able to achieve very pure hydrogen, so high hydrogen purity. Of course, for that, you will have to use a hydrogen purifier. So I'd like to look at just a typical containerized PEM electrolyzer system, and just going to run you through it. So we've got the air blast cooler on the top here. We've got the refrigerant chiller over here. We've got rectifier, transformer rectifier over here. The water purification system is going to be inside this container here. We will also have the stack inside the container. Hydrogen water separation, oxygen water separation inside the container, and hydrogen purification system is also going to be inside the container. Right, so this is a Nel electrolyzer. Let's look at a different one. So of course, this is going to be so much different. We're going to have an air blast cooler. We're going to have a refrigerant chiller, which is over here. Of course, the air blast cooler is over here. Rectifier. So the rectifier is going to be one of these containers. It's going to be likely this container on the right-hand side. The water purification system is going to be inside of the container. The stack is, of course, going to be inside the container. Hydrogen separation inside the container. Oxygen separation, hydrogen purification system, etc., all inside the container. So this is another PEM system, another containerized PEM system, but it's from a different manufacturer. And then this is another system. Of course, this is from Plug Power. And what is the difference? The difference, these systems are very similar. They are typically so similar that you will have the air blast cooler outside here. You'll have the refrigerant chiller, the transformer, etc. So these systems are relatively similar. They're going to differ slightly. You're going to have different materials used. You're going to have different designs. Some designs, for example, will allow higher water flow across the stack, etc. However, these systems are relatively similar. So what I'm going to do in this webinar is I'll be talking about these systems, what we will see in a typical electrolyzer system. Obviously, things will differ system by system, but just typically, I will go into what we see typically in these systems. What about a very large system? So what about a multiple megawatt scale system? So again, we're going to have an air blast cooler. I've got this little star here because I know people are going to say, yeah, you can't see the air blast cooler here. No, you can't see it on this diagram. Also, the refrigerant chiller is outside of the scope of this diagram, but we've got the rectifier and the transformers. You can see the rectifiers and the transformers over here. You can see the water purification system over here. You can see the stacks. Of course, there's all this, all of the stacks are all located here. And we have the hydrogen purification, the oxygen purification, sorry, the hydrogen separation and the oxygen separation. So that's what these vessels are going to be for. And we've got the hydrogen purification system, which is going to be which is going to be a temperature swing desiccant dryer, which is located over here. So let's look at a typical a PFD of an electrolyzer. So this is pretty typical for a 1 megawatt system. So we've got the stack over here. Let's start from the beginning. So for a 1 megawatt system, and you know, this is going to vary, of course, but for typically, this is pretty typical. You will have around 325 liters an hour of water, and this is going to be, you know, we're assuming that this is potable water, could be tap water, flowing into the water purification system. And we'll come back to how the water purification system works shortly. But there will be this water flow going into the water purification system. There's going to be reverse osmosis membranes. And from the reverse osmosis membranes, we are going to have around 125 liters per hour drained. And this is going to be this will just be wasted pretty much. It will typically just go to drain. We will have around 200 liters of purely of highly pure water. And you know, we're talking about very close to the lowest conductivity of water. So it's going to be around 0.08, 0.09, or 0.1 microsiemens per centimeter of water conductivity going into the oxygen water separation vessel. And from the oxygen water separation vessel, we are going to have around 1,200 liters per minute of water flow. And this is approximate. So some electrolyzer systems will, so this number will be 1,500, or others it might only be 1,500, and some might only be 1,000 liters per minute. And typically, the higher, the better for the water flow rate per megawatt. And we'll come back to that shortly. But let's just assume 1,200 liters per minute of water flow. What we have to understand here is this 1,200 liters per minute of water flow. Most of this water flow will come right back into the oxygen water separation vessel, and we will just have this flow of water circulating. And most of the water that will go into the PEM electrolyzer stack will come out. So by mass, when you're running at 100% output at on a 1 megawatt electrolyzer, typically around 99% of the water will come out as water, and only about 1% per mass will be so did I say 99? About 99.8%, sorry, about 99.8% will just will of the water that went in will also come out on the other side, and only about 0.2% is going to be used for the reaction at each cycle of the water going around. So actually most of the water is used to either wash away chemicals or cool down the PEM electrolyzer stack. Of course, the oxygen evolution reaction and some on the hydrogen evolution reaction so the oxygen evolution reaction is requires quite a lot of energy. There'll be quite a lot of inefficiencies especially in the oxygen evolution reaction, more so than the hydrogen evolution reaction, and therefore that will require cooling, which is why when the water and of course we'll have some oxygen in here as well, and we'll talk about how much oxygen we'll have over here later. But the water coming out of the stack will pass through a plate heat exchanger typically, and the water will get cooled down. Then it will go into the oxygen water separation vessel, and then the cycle will just repeat over and over again. And we have, of course, a power supply, and this particular situation, it will be around, it will be a power supply of around 1 megawatt, because it's a 1 megawatt system. Of course, the power supply will include several things. You will typically have a transformer. You will also have a rectifier. Of course, this is very much simplified. So, of course, we will need a rectifier because, well, electrolysis only works with DC power. It does not work with AC power. And the rectifier takes alternating current, and it will convert it into direct current. And normal operation in a PEM electrolyzer, you are going to have water transport from the anode side, which the anode side is the water and the oxygen side. So the water flows through the anode side, and on the cathode side is the hydrogen. So the green line here shows the flow of the hydrogen. But in normal operation in a PEM electrolyzer, we are going to have water flowing over to the cathode side, and this is completely normal. And this water flowing over to the cathode side will go into the hydrogen water separation vessel, and the hydrogen will bubble up to the top, and the water will stay on the bottom. And we'll come back to this later also. But so this water, still relatively good quality water, which we can reuse with relatively little polishing required. And then from there, the hydrogen flowing out of the hydrogen water separation vessel will flow into the oxidizer. But remember, this hydrogen is still going to be saturated with moisture, so we're going to have a drier system. So this is going to be this is typically going to be a temperature swing desiccant drier, and from there the hydrogen is going to be highly purified hydrogen, which will then go to our client. So the hydrogen coming out of the hydrogen water separation vessel will have to go into a hydrogen vent, or we will need to put the hydrogen through some sort of a process in order to rid the hydrogen bubbles out of this water, because we cannot send any hydrogen back into the water purification system for safety reasons, and for obvious safety reasons as well. Okay, conscious of time, we've got to move on. So we'll look at the PEM electrolyzer cell. So we've got the anode side on the left-hand side here, cathode side on the right-hand side. So we've got water going into the anode side and water and oxygen coming out on the outlet of the anode side. And what we have here is the hydrogen. So once we apply the DC power and we reach the minimum voltage, which is so the minimum voltage called the threshold voltage is 1.48 volts, of course. And once we reach the threshold voltage, something very interesting will start to happen. So because hydrogen is P positive, and so hydrogen, and excuse my terrible drawing here, but having to do this with a mouse. So this is a proton in the middle, and then we've got the electron, which is the E minus up here. So once we split off the E minus, once we split off the electron, the proton is going to be extremely tiny. This proton, because it's so tiny, it's small enough to go through the PEM membrane. And the proton is positively charged. The anode side is positively charged. Therefore, the anode side will repel the positively charged proton, and the cathode will attract the positively charged proton into the cathode chamber. And once the proton goes over to the positive, goes over to the cathode chamber, And the electron, by the way, the electron goes through the electrical connections over to the other side. Proton and electron will meet, and one proton, one electron, that will form a hydrogen atom. And of course, or almost immediately, once we have two hydrogen atoms, that will form an H2 molecule. And we have a few other things here as well. So we don't only have, as in this situation, we don't only have hydrogen going over to the cathode side. We also have we also have water transport over to the other side. The way I imagine this is, just imagine the PEM membrane to be a sponge, and if you hydrate the one side of the PEM membrane, if you hydrate the one side of the PEM membrane, the water will go over to the other side of the PEM membrane. This is completely normal because so electrolysis will not happen unless the PEM membrane is hydrated. Of course, the PEM membrane has to be hydrated. And yeah, so because of that, we have quite a lot of water making its way over to the hydrogen side, over to the cathode side, and that is completely normal. And there are two mechanisms. There are two ways for the water to go over. One is diffusion. So if you have water on one side, you will have water on the other side because of diffusion, high concentration to low concentration, as well as electroosmosis. So what is electroosmosis? Well, electroosmosis happens whenever we're electrolyzing. So electroosmosis is proportional to the current density. So the higher the current density, the higher the rate of electroosmosis. So i.e., the more hydrogen we're generating, the more water we're also putting or the more water is being transported over to the cathode side via electroosmosis. And you can see this this arrow in here which says water. This is optional. So this is not really being done by most OEMs. However, there are one or two OEMs that I can point to which do run water into the cathode side. Yes, they do this. This is a thing. They do run water into the cathode side. And by the way, this is not only for small electrolyzers, also large, some electrolyzer OEMs with very large megawatt scale electrolyzers, or even gigawatt scale electrolyzer. So even companies that are, even OEMs which are aspiring to build gigawatt scale electrolyzers do this. Why? Because they've realized that cooling one side, it's great if we cool the anode side because of the oxygen evolution reaction, but there's also some heating generated by the hydrogen evolution reaction. Therefore, some OEMs do actually pump some water to cool down the hydrogen side as well. Okay, so we've got to move on. So of course the stack is over here. We've got the water going in, the water going out, the hydrogen going out, and the power supply unit connected. Next up, we'll look at water purification. In short, the water purification system is it's a carbon and a particulate filter, and there'll be an element of water softening, and there'll be reverse osmosis. And after the reverse osmosis, we'll see the conductivity of the water drastically reduce, but not quite enough for PEM electrolysis. So, and by the way, PEM electrolysis. So, depending on what you read, some people tend to think that PEM electrolyzers can basically get away with water conductivity of about 5 microsieverts per centimeter. This is wrong. The lower the conductivity, the better for the stack. Less than 1 microsievert per centimeter would be fantastic. Even 0.5 microsievert per centimeter is completely achievable. Yeah, 5 microsiemens per centimeter. If you were to run the stack at 5 microsiemens per centimeter, it will come to end of life very shortly. Trust me. For that, to reduce the conductivity of well, the purity of the water and the conductivity of the water, you would need the mixed bed DI resin, and the mixed bed DI resin, it will so downstream of the mixed bed DI resin, you're going to see water conductivity levels that are very, very close to the theoretical lowest conductivity of water, which is 0.056 microsiemens per centimeter. So you won't see it go that low, but you can achieve 0.08, 0.09, or 0.1 microsiemens per centimeter downstream of the DI bed resin, or mixed bed DI resin, sorry. So there are two parts of the water purification system. So typically, what you'll see is you'll have, of course, the water inlet, and you will have what we've just talked about here, this water purification system with the activated carbon filter, the particulate filter, reverse osmosis, etc. And the role of this water purification system is to get you from your potable water over to the water that you can actually use, or from your tap water to the water that you can actually use in your PEM electrolyzer. However, what you will also see, yes, get my laser pointer. No, so what you will see is when your water passes through the stack, you'll have something very interesting happen. This water going into the stack will be highly pure water, but coming out of the stack, the water conductivity will increase. You will essentially have muck in the water. There's a few things. One is fluoride release. And by the way, one thing to know about fluoride release is the rate of fluoride release is actually quite high at low current densities, contrary to common belief. You in addition to that, you will also have impurities, especially in brand new stacks. When you fit a brand new stack, the water coming out of the stack will increase in conductivity. So what do we do? Well, there's two ways we can fix this. So, well, both ways would include one part of the water purification system. Some systems would send the water back with a repolishing pump and back into the water purification system. And then, so some of this water, approximately 1 to 10% of the water that's going through the main circulation pump would also be circulated back into the water purification system to be repolished. There's another way to do this. And by the way, just another thing on this, the water that's going back into the water purification system from to be repolished will not go through all of these steps. It will only go through the mixed bed DI resin or something else, which we'll come to in a second. I can already see we're going to go over time here because I've barely started and we're already I only have 2 minutes to go. We're going to go over a little bit. Sorry, guys. So the other way to do this is, instead of having a repolishing pump here, there's going to be a completely separate water polishing loop. So there'll be a pump. Excuse me for my terrible drawing. And then there'll be a water repolishing system here, and then the water will go back into the oxygen water separation vessel. Okay, so the water polishing can be done in two ways. And this is a relatively recent development in the PEM electrolyzer sphere. And what a lot of electrolyzer OEMs have been looking at is, of course, DI resin is what we've been using for a long time. You can also regenerate DI resins, but that has not been done in PEM electrolysis. And not that a lot of companies haven't looked at regenerating the DI resin catalyst, um, but yeah, it just hasn't really been done in PEM electrolysis to this point. So what we have to do is every so often, every, let's say, 6 months or 8 months, 4 months, you would have to go on site and replace the DI resin inside of these containers. And the trouble with that is, of course, it increases maintenance, and also it's a cost. And what a lot of OEMs are doing now is providing an option for electrodeionization, which is what you see on the left-hand side here, electrodeionization. And electrodeionization does not require any replacement of material, replacement of parts, etc., because it just uses DC electricity to polish the water, and therefore it saves costs. So most, like I said, most OEMs, if you speak to 5 OEMs, 3 of them will provide you with an option for electrodeionization. Okay, let's look at oxygen and hydrogen. So oxygen separation and hydrogen separation quickly. So first thing to notice is, get my pen. So first thing to notice here is that the water going in. So this is the water going into the stack, and I'm hoping that this helps with making it quite clear. But 100 out of 100% of the water going into the stack versus the, like we said, the 99.8% of the water that went in that also is coming out of the stack. So we have a reduction in the water of 0.2%, because that this 0.2% of the water has been turned into hydrogen and it has been turned into oxygen. Now, here's the thing. While we have a slight reduction in the water that's coming out of the stack, we have a massive increase of the volume that we have to wash out of, that we have to transport out of the stack on the cathode outlet, on the anode, sorry, on the anode outlet. So what you see here is the oxygen will, so out of the 0.2% water, the oxygen that we've generated increases this volume by 38%. So actually we have to wash out, or we have to transport out a lot more volume than we've put in. Because we, of course, we have a lot of oxygen in this stream leaving the stack. So again, the water goes into the stack. Now the water, when the water comes out of the stack, it will be filled, or there'll be a lot of oxygen. In fact, if this was a clear tube, what you would see is around 38% of what you'd see in that tube would be oxygen, would be oxygen bubbles. And these oxygen bubbles and the water will go into the oxygen water separation vessel. And this oxygen water separation vessel will have water, let's say at this level. The water will go into the, into the bottom of the vessel, and the oxygen will exit on the top here. And of course, you know, there is a little bit of hydrogen here as well. I get that. Which is exactly why it's very important, for one, that the oxygen vent is at the top of this vessel, because of course there'll be, well, let's say up to 2% or up to 1.8, 1.9, or maybe even 2% hydrogen in this vessel at low current density. But the point is, the water will go down to the bottom, and of course, any bubbles in the water will come up to the top. And it normally takes about 15 to 30 seconds for the bubbles to come up to the top and for the water to go down to the bottom. And the whole cycle just repeats again. And so the pressures here in the oxygen water separation vessels, so some systems still would use the atmospheric pressure. So the essentially the oxygen water separation vessel will just simply be open to atmosphere. Yeah, some systems still tend to do that. Others have increased the pressure ever so slightly to well, to up to about 2 or 3 bars. And so it's quite low pressure. You don't want to go very high with this pressure, but you'll achieve a few things if you don't have the oxygen water separation vessel open in the atmosphere. One of the things you'll achieve is it prevents impurities coming in. So it prevents the ingress of impurities. And what you will also have is you will have a slightly better recirculation with a slight positive pressure. That is for a few reasons. And by the way, one of the reasons is that on the surface of the membrane, the bubbles will be smaller because you have that ever so slight increase in pressure. Therefore, you're covering a larger surface, a larger area of the membrane surface. And let's look at hydrogen water separation. So, like we said, it's completely normal for the PEM membrane to allow water to cross over to the other side of the, well, to the cathode side of the membrane. And we've got the hydrogen water separation vessel being at the pressure of the hydrogen. So it's at running pressure. And typically the running pressure is going to be 30, maybe 32 bars, or maybe even 35 bars on some systems. But 30 bars is typically the industry standard. And what you will have is this water that's being reused, because this is still pretty good water, which all we have to do with this water is run it through the water purification system in order to repolish the water. But before we do that, there needs to be a method for us to remove the hydrogen bubbles, because if you remember, this is at 30 bars. And because it's at 30 bars, when you reduce this pressure, you know, when you reduce this pressure down to atmospheric or just slightly above atmospheric, a lot of bubbles will get released, and those are going to be hydrogen bubbles. And this hydrogen must be vented safely. And there are some pretty complicated systems pretty complex systems, I should say, that which would safely vent out the hydrogen out of this recirculated water, out of this water that we're reusing here. And then, of course, the hydrogen that is going to the dryer is going to be very close to 100% relative humidity. So there'll still be quite a lot of water, or quite a lot of liquid water. Sorry, not liquid water. Water vapor in this flow of hydrogen, and therefore this flow of hydrogen will go to the dryer. So and we can see this on the larger scale. So we've got the dryers downstream, the oxidizers, etc. So lastly, we'll look at the cooling systems. So there are a couple of different cooling systems on these electrolyzers. We've looked at one system typically uses air blast coolers, and the other system typically uses refrigerant coolers. And what we see here is going to be the cooler in order to cool down the process water. So you'll use this to cool down the water that is used for the electrolysis process. This is the water that we are putting through the stack. So we've got a plate heat exchanger like we've looked at. And of course, we've got an air blast cooler. A few things on this. For example, if you have a larger air blast cooler, of course, your capex is going to increase, but you will likely have to run the fans for a shorter period of time each day. Therefore, your OPEX will be reduced. And also, depending on what material what type of air blast cooler you use, if you're away from the shore, for example, at least 2 miles from the shore, on land, of course, then you're able to use the normal copper air blast coolers. If not, so if you're very close to the shore, then you will likely need a different material such as stainless steel, etc. And because it's a different material, the air blast cooler is then going to be less efficient. Therefore, you'll need a larger air blast cooler, which will increase your capex, your OPEX, etc. So on some systems, what we're seeing is, and this is especially used in relatively large electrolyzer systems, and on relatively warm or even hot climates, is adiabatic coolers. And what is an adiabatic cooler? Adiabatic cooler, on the left-hand side, you can see a normal air blast cooler. The right-hand side, you can see an adiabatic cooler. The difference is that the adiabatic cooler has this has a sprinkler system. So you can see these lines here, these are sprinklers. And what this does is the air inlet into these, into the grill, we draw it, will be pre-cooled because as you're spraying this water into the inlet air, you're going to pre-cool the air. And so, for example, if the outside air temperature is like 38 degrees Celsius and your wet bulb temperature is only going to be about 23, 24 degrees Celsius. Therefore, you're able to pre-cool the air to to approximately 23, 24 degrees Celsius just by this sprinkler system. And of course, we saw this. We've got the air blast cooling plate heat exchanger over here, just for context. And the cooling system that we've talked about before for the refrigeration cooler. So this is going to be the cooling system for the hydrogen purification system. So there is there's actually quite a lot of research going into reducing the size of these refrigerant coolers, or even moving from refrigerant coolers into air blast coolers. Why? Because of the fact that refrigerant coolers are very expensive. The OPEX and the CAPEX are very expensive, and we are wanting to put as much electricity into the electrolyzer stack and not into the balance of plant. Okay, yeah, this is where we are for context. So for the refrigerant cooler, we are going to be cooling down the heat exchanger for the dry vessel A and dry vessel B. Okay, so with that, we'll jump right into the questions. So the courses that I do are the Principles of PEM Electrolyzer operation training course, and this is typically held in person in Kuala Lumpur. And another training course that I do is the stack design, development, and operation, of course, for PEM Electrolyzer stacks. And the next course is going to be in April, also in Kuala Lumpur, and electrolyzer plant design is another upcoming course that we are working on right now. And with that, we'll jump into the questions. Mai, do we have any questions?
Yes, we have a lot of questions here. So first one is, basically it is similar to alkaline electrolyzer. So
Sorry, can you repeat the question, please?
questions from the it is similar to alkaline electrolyzer.
So is the question, is PEM similar to alkaline electrolyzer?
Yeah, I think so. It is referring to that because this is posted the first slides that you discussed.
Okay. Well, PEM. So is PEM similar to alkaline? No, no. Of course, it's electrolyzer. It's a different. It's an electrolyzer. It generates hydrogen, but that's about it. In alkaline, you can only run an alkaline electrolyzer at low current density. You're going to struggle to ramp it up or ramp it down very quickly, so you can't really use it for grid balancing, and also you're using the chemical potassium hydroxide, which you have to mix with water at approximately 25 to 30% potassium hydroxide and water. So it's not very similar.
We also, we also have here how to avoid intermixing of gases in the electrolyzer itself if they don't get separated by any reason.
So we don't mix gases. So we don't separate gases. We separate water from the hydrogen, and we separate the water from the oxygen. And the electrolyzer stack is where the reaction happens. So you have water on one side, and the oxygen will stay on one side, and the hydrogen will go over to the other side. But there's no situation where the gases won't separate. There could be a situation where if there is damage on the stack, that's the hydrogen, so the cathode side is pressurized, and if there's damage, the hydrogen can potentially go back into the anode side. And there are so most systems, there are extensive monitoring of the oxygen water separator to make sure that the hydrogen level doesn't go too high. Is there any
Yep.
other
Also
more
here,
questions,
what
Mike?
is the system? What is the system efficiency of PEM for hydrogen production?
So if you don't include so the voltage efficiency, if you don't include heat recovery, it can be anywhere from 60% to 70%. 70% efficiency is quite high efficiency, 60% efficiency is relatively low efficiency, anywhere in between. To generate 1 kilogram of hydrogen, you will typically use between 50 to 55 kilowatt 50 to 55 kilowatt hours of electricity to generate 1 kilogram of hydrogen, and 1 kilogram of hydrogen contains 33 kilowatt hours of energy. So therefore, it's going to be around 60 to 66, potentially even 70% efficiency on very high efficiency electrolyzers. Yeah, if you include heat recovery, you can achieve very high efficiencies, but very few systems include heat recovery. So you can read about 80% efficiency on PEM electrolyzers, and that is going to require heat recovery to be included in that calculation. Are there any more questions, Mai? I don't think I can hear you, Mai, if you're speaking. Okay, let me just see myself. Where are we on here with the questions?
Okay, hi, I'm here. I just
Okay, do you have any more questions, Mai?
okay, we have here what is power consumption, PJ, hydrogen, and PEM?
Sorry, can you repeat the question again, please? I'm not sure if I understand the question.
What is what is power consumption, a kilogram, hydrogen, and PEM? I think KJ is kilogram, right?
52 kilowatt hour, 52 kilowatt hours per kilogram is quite typical. 50 to 55. Like I said in my earlier question. So the next one is large type of PEM available on market. Well, yes and no. The largest PEM electrolyzer today is 24 megawatt, and that's over in Quebec in Canada, and that is the largest currently operational PEM electrolyzer in the world. There are I've seen an announcement for where a company was aspiring to build a 1 gigawatt electrolyzer. So that is a very large electrolyzer, and I've seen some of the clients that I work with are looking to build 3 gigawatt of electrolysis. That's 3,000 megawatt of electrolysis by 2030, which is of course a lot of electrolysis. But at the moment, the largest electrolyzer that anybody has built that is operational is 24 megawatt. The next question I can see here is PEM membrane is hydrated with water or some electrolyte. PEM membrane is hydrated with pure water. There's no electrolyte on the surface of the PEM membrane, so that is being circulated through the PEM. So PEM itself stands for proton exchange membrane, but it also stands for something else. PEM also stands for polymer electrolyte membrane, which means that the membrane itself is the electrolyte. So we don't actually need to flush anything on the surface of the membrane. That is an electrolyte. All we have to flush is very pure water on the surface of the membrane. Therefore, we don't need an electrolyte in PEM. The next question, great questions, by the way. Where are the rare earth minerals being used in PEM? Well, there are several different locations which we can mine, where we can source iridium for the anode side, and platinum for the cathode side, iridium oxide and platinum. Actually, iridium is from stardust. It's not even originally from Earth. Okay, next question is power consumption per kilogram of hydrogen in PEM. I think I answered that around 52 kilowatt hour, approximately, depending on what system you're looking at. What amount of kilowatt hour required to produce 1 kilogram of hydrogen? Again, about 50 to 55. Lifetime of a PEM electrolyzer in comparison to alkaline electrolyzer. Great question. Nobody knows. This is actually a really good question. So OEMs typically all are telling us that their system will last for 80,000 hours. Show me one PEM electrolyzer that's a large-scale PEM electrolyzer, and in the megawatt scale at least, and it has lasted. It has provably been running without a stack failure and without any major failure on the balance plant for 80,000 hours. You cannot show me one, and if you do, well, you just can't. So it's interesting. Alkaline electrolyzer, we have a bit more data, but there's also issues with alkaline electrolyzers. If you look at the world's largest alkaline electrolyzer system, you'll know exactly what I mean. The one in China by Sinopec. Just Google that. But that is interesting. I believe that PEM electrolyzers will get to a point where by implementing redundancy systems and systems to improve reliability, that PEM electrolyzers will increase in their lifetime, and they'll overcome some of these issues. What will be the efficiency and purity of PEM Electrolyzer. The voltage efficiency we've talked about, and the purity is so depending on your dryer, you can easily achieve grade E hydrogen for fuel cells, and you can easily get to the point of one part per million, 1 ppm. You can get to that point. And I'm talking about 1 part per million, water vapor. What about oxygen content? If you're also asking about oxygen content for the purity question, so 5 ppm of oxygen is what a lot of uses are looking for, but that's very difficult to reliably achieve. And you can say, okay, you can achieve it most for for most parts of your 24-hour day, but sometimes it will peak over that. It's very important. It's very difficult to keep that constant. But 10 ppm of oxygen in the hydrogen is easy to achieve. And like I said, 1 ppm moisture. Next question: demineralized water amount to produce 1 kilogram of hydrogen, about 9 liters. Am I right in saying that? Let me have a think. Yeah, 9 liters. 9 liters of water. 9 liters of pure water will generate 1 kilogram of hydrogen for you. When will it be possible to construct 20-megawatt PEM electrolyzers? Already happened. 20 megawatt. Just look at the Air Liquide site built by Cummins PEM Electrolyzer over in Quebec, Canada. 24 megawatt. Next question: why heat exchange provides in the outlet of PEM, but not in the inlet? Interesting question. One of the reasons is because you want to cool it down. You want to cool the outlet down, so you're not having to run this water and hydrogen through pipelines, which are quite hot pipelines for very long. Basically, you don't want to put your hot water into the oxygen water separation vessel. You want to put you want to put cooler water into the oxygen water separation vessel. However, it's an interesting question. Some OEMs will do it one way, and others will do it another way. I've seen electrolyzer systems where it's in the inlet, so the cooling is actually at the inlet. Control philosophy for pressure of electrolysis. I'm not sure if I understand this question. If you'd like to rephrase that question, Rahul Saini, I'm not sure if I understand it. I do apologize. How hydrogen at pressure is generated in PEM? It's yeah, that's an interesting question. So on the cathode side, so you've got the membrane in between, and the hydrogen atoms will start to appear on the cathode side, and as they're appearing on the cathode side, there's going to be more and more hydrogen molecules, and there's actually a back pressure regulator, or you can also call it you could also call it a pressure control valve, which is downstream, and that is controlling the pressure on the cathode side of the stack. It's interesting because the higher the pressure you go, the more voltage you'll be running at the same current density. So again, let me just explain this. So if you're running an electrolyzer at a set current density, then and you're running at, let's say, 10 bars, then your voltage is going to be lower versus when you're running at the same current density, you're generating the same amount of hydrogen, but you're running at 30 bars. So your voltage will go up. That's where the energy goes in to generate that pressure for you. Okay. Okay. How to developer decide the operating pressure of PEM? What are design basis for operating pressure? So what we see at the moment is the operating pressure is typically 30 bar, and this is so this is an industry standard. sort of thing. But I think what we will see in the future is, in order to reduce wear and tear on the stack, because essentially the higher the pressure for the stack, the less time it lasts for. It's similar to when you buy a car and you're putting your foot down, you're driving your car at 100 miles an hour down the motorway all the time. It's going like you won't have that car will break sooner than a car that you're driving moderately. So what a lot of large scale electrolyzer customers are looking at is, what they're saying is, we don't need this hydrogen at high pressure. So for example, let me give an example. Ammonia. So ammonia-based fertilizers require a lot of hydrogen to produce the ammonia, and also refineries, they need a lot of hydrogen, and those customers don't really need the hydrogen to be at very high pressure. So they're saying, why don't we reduce the pressure and have the stack last for a longer period of time, as well as reducing the increasing the efficiency, i.e. putting in less electricity and having more hydrogen out. So it's difficult. At the moment, most electrolyzer systems will be 30 bars. What is the operating temp? POE, I'm not sure if I understand what POE is. So what is the operating temperature? The operating temperature is going to be different system by system. A very typical operating pressure is 60 degrees Celsius, but some OEMs would have the operating temperature at like, let's say, even 50 degrees Celsius, and some would have it at 65 or even 67. The trouble is, the higher you go, the more risk of membrane degradation on the stack. So the higher the temperature, the more risk of basically hotspots on the stack, which is one of the main degradation mechanism of PEM stacks. And the trouble is and also the higher you go, the more flow rate release. Yeah, and then also the lower. So if you're in the lower end of the scale, your electrolyzer will be quite inefficient. The higher the higher the temperature, the more efficient it is. So actually, for you to run a PEM electrolyzer at 90 degrees Celsius, and of course, people are going to say, that's crazy, nobody does that. Yeah, of course, nobody does that. But your electrolyzer will be very efficient. It wouldn't last for a very long time. Everything will melt very soon, but it will be quite efficient. What is the life of the membrane in PEM? Yeah, like I say, if you listen to the hype that the OEMs are trying to tell you, it's 80,000 hours. I can show you some other, some other people talking about it being much less than 30,000 hours, and I can show you some others being even more pessimistic and more realistic with things. This is something that is not really. We don't really know, because the OEMs won't brag about their electrolyzers lasting for not a very long time, so you don't really know. And I wouldn't like to guess. What is the life of the membrane in PEM? I understand the oxygen and hydrogen separation, but how do you separate the oxygen water which is generated on the anode? You just let the oxygen bubble up to the top. The oxygen is going to be gaseous, not liquid, of course. And the oxygen will just go up to the top, and it will bugger off out the O2 vent, and the water will stay on the bottom. What is the cost per kilogram for PEM? I'm not sure if I understand the question. The cost per kilogram of hydrogen, or the cost of for the cost per kilowatt for PEM. Ravikant Sankey, do you mind? Maybe it's just me misunderstanding the question. Do you mind rephrasing that? That would be great. I understand the oxygen, but how do you separate? Yep, I got that. What is the cost of 1 megawatt of PEM and alkaline water electrolyzer? So here's the thing. Prices have massively been varying. In fact, what we've seen in the past 12 months is a massive increase um, in the prices on both PEM and alkaline electrolyzers, especially in the West. Um, and it's hard. So let me just give you a number for PEM. 1 megawatt is going to be £1 million or $1 million, or between a million and 1.2 million. Although you've seen an increase of that recently. Some OEMs have gone up as much as 50 or 55%, but most have gone up about 30% in their prices. How do they decide operating pressure and temperature of electrolyzer? So your OEM is going to decide that. If you are an OEM, how do you decide operating pressure and temperature of electrolyzer? Well, the way you decide is, like I said, 30 bar is going to be sort of industry standard, and potentially you can promise to your client that you can reduce the pressure and increase the lifetime, things like that. The operating temperature, again, this will just vary design by design, and it is going to. So how do I design that? How do I decide that? I will decide that by knowing what components I use inside my stack and what materials those require. And if I have components inside my stack that are, and that won't do very well over 60 degrees Celsius, then I either change those parts, or I review the temperature. So max conductivity of water for operating PEM. Well, this is a question where so you can run your PEM electrolyzer on tap water quality, but it's just not going to last for a very long time. You might as well throw it in the bin if you did that. You will generate hydrogen, but it won't do that for very long. For you to have an electrolyzer that lasts for a very, very long time, you must have the water conductivity at around 0.5 microcentimeter at all times. Chronicity of PEM. Well, interesting. So most electrolyzers will have a typically a current density. The current density is going to be around 2.5 to 4 amps per square centimeter as the maximum current density. The minimum current density is typically going to be between 0.5 and 1 amp per square centimeter. However, we're seeing electrolyzer manufacturers like Electric Hydrogen, for example. Well, electric hydrogen is famous for this, is to increase the current density up to 6 amps per square centimeter, and they're talking about really increasing it to 11 amps per square centimeter. The trouble with increasing the current density to a very high current density is that your stack degradation will go through the roof unless you have some mitigating measures. And even if you have mitigating measures such as increasing water flow, reducing water conductivity, perhaps even increasing the pressure a little bit on the anode side, things like that, and maybe even cooling of the cathode side, then so unless you do that, your stack degradation will go through the roof. Where are we with the questions? I think I lost my place here. Maximum activity, current density of PEM. Yeah, the current density, like I said, it will be 2.5 to 4 amps per square centimeter typically, and some will go crazy. Yep. Is it only 0.5% water of the total water input converted to be hydrogen in PEM? No, so the way it works is you're pumping the water through, and each pump, so every minute you're pumping, let's say 1200 liters a minute. So at each cycle you're going to so out of each cycle you're going to use up about 0.2% of that water when you're running at when you're running at 100% output. And last question that I have here is how much actual power is required to run the PEM. So I've kind of answered this before, but I have something else to add. An average is going to be 52 kilowatt hours per kilogram of per kilogram of hydrogen, and about 10% of this is going to be the balance of plant, or up to 10% is going to be the balance of plant. And of course, you want this to be as low as possible because the balance of plant isn't generating any hydrogen for you. So 52 kilowatt 52 kilowatt hours, so between 50 and 55 kilowatt hours per kilogram of hydrogen is quite typical. I hope that answers everybody's questions. Feel free to find me on LinkedIn and DM me if you have any further questions. But yeah, thank you so much, everybody, and I hope you've enjoyed the webinar. Yeah, all the best. Take care.